Hello everyone. Namaste. Good morning, good afternoon, and good evening. Well, it is evening here in Nepal. We have just started at sharp 8. That is GMT plus 5:45. Hope you all are doing good. This is Suraj Gautam, a civil engineer and DRR professional from Institute of Himalayan Risk Reduction, and I'll be your host for today's session. Institute of Himalayan Risk Reduction has been regularly organizing the webinar series on disaster risk reduction, where we have successfully organized two webinars. The first one was related to the DRM initiatives in Asia Pacific, while the other one was related to flood early warning system in Nepal, which we concluded just yesterday. And today we are starting our brand new series, that is the webinar series on Geo-Science for Sustainable Development, which will be organized in a regular basis. So I would like to welcome you all to our very first session of our first webinar on Geoscience uh, for Sustainable Development. In this webinar series, we'll be hearing the healthy experiences from geoscientists, and today we'll be discussing on where did the India-Eurasia collision take place. On behalf of the organizing team, we are really grateful to our guest speaker, Dr. Upendra Baral, who will be sharing us with his insights and healthy experiences.
Thank
So
you.
we would like to warmly welcome our speaker, Dr. Upendra Baral, who is an associate professor of Institute of Tibetan Plateau Research, Chinese Academy of Sciences, China. The session will be moderated by Assistant Professor Dr. Vasantaraj Adhikari from Institute of Engineering, Tribhuvan University, who is also the visiting scientist of IHRR. It is indeed an honor to have insights from our distinguished speaker. Also, we'd like to welcome all of our distinguished guests and participants who are attending this session. We are very much pleased to share that we have received amazing responses for this webinar. We have had like more than 150 registrations on the very first day of the release of our webinar poster. And till date, we have more than 300 registrations throughout the globe. So to address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction. We will be receiving the queries and feedback from our Zoom chat box as well as from our social media live streams. So before starting our series for today, I would like to share some brief introduction about us. IHRR is a research institute established with an objective to assess and understand the risks to contribute for the sustainability. Complying with the Sendai framework for disaster risk reduction, IHRR envisions to understand the risks and application of interdisciplinary knowledge with science, engineering, technology, and innovations to contribute for risk reduction and bridging of academic research with professionals and policymakers for the sustainability. Our team consists of dynamic professionals with expertise and experiences in the field of DRR in understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. So we'll be sharing some works that has been done by IHRR. Uh, so far, we have successfully accomplished a transdisciplinary project that is a landslide risk assessment on Sino-Nepal road corridors. Similarly, we have had a quite number of engagements on this COVID-19 response, from developing swab collection booth to medicine carrying robots. Similarly, we were also involved in the organizing in the development team of the national portal of Ministry of Health and Population. So we have collaborated with local governments to bring out UAV surveying of Hetauda sub-metropolitan city for the very first time. And this was done during the lockdown period so that we had some minimal disturbances. Besides this, we are also advocating the recently promulgated DRR Act 2017 and trying our best to collaborate and contribute. Our initiatives, our voluntary initiative was also featured in the Sendai voluntary commitment, as you can also see in the website. Similarly, as I have already mentioned, we have started our webinar series. So this is our the brand new series on geoscience for sustainable development. So we'll be starting without further much delay. I would like to continue. And I would like to share some house rules for this webinar. The audio and video of the participants will be switched off. For any queries, the participants can write up in the chat box or in the comment section of Facebook streaming live. The waiting rooms will be enabled. and only registered participants will be allowed to enter the webinar due to some security reasons, and the overall session will be recorded. So without any delay, I would like to move on to our session, and may I request Dr. Basantaraj Adhikari to proceed further with his moderation. Thank you.
Thank you, Suraj. Am I audible?
Yes, sir, you are audible.
Thank you, Suraj Gautam, Executive Director of Himalayan Risk Reduction. It is indeed my pleasure to moderate this session of my esteemed colleague, Dr. Upendra Baral, and we have studied together and we are doing research together for a long time since our university days. And Dr. Upendra Baral has already achieved, so many, high rank of publications, and then achieved world recognition around the globe. And he has started his master's and bachelor's in Tibet University in the Department of Geology, and then he started his PhD at the Institute of Tibetan Plateau Research, Chinese Academy of Science under the Castras Fellowship, and then he started working as an associate professor after that at the same institute, Institute of Tibetan Plateau Research. This research institute is really recognized for producing really good or high level of research, not only in the Himalayas, but also in the other part of the world. And Dr. Baral is really focusing or devoting his research for more than 2 decades in this region, starting from Western Himalaya, Central Himalaya, and then to the Eastern Himalaya. So working from Western syntaxis to the Eastern syntaxis, how and when or where this kind of, the collision took place between this Indian plate and Eurasian plate. So this talk will be highlighted, he will highlight some of his recent advancement on that, and he has already published more than 25 scientific research papers in peer-reviewed journals, and he has published more on other journals also. And he's a very well-recognized researcher in the geoscience field or earth science field in Nepal, along with the other part of the world. So he, among our colleague or for the new generation, is one of the go-to people, so people, they want to be like Upendra Baral. So I'm very, very pleased to invite Dr. Baral for this webinar series that Institute of Himalayan Risk Reduction has started. So the aim of that is to bring the prominent or eminent experts from, not only from Nepal, but also from other part of the world, who are working in geoscience field, mostly focusing on Himalayan region. So today is the first webinar on that series, and I'm very happy to welcome Dr. Baral. And so after his presentation, we'll have a Q&A session, but as Suraj Gautam has already explained or described, you can just write your questions in chat box or in Zoom or in social media, in Facebook, that we'll address after the presentation of Dr. Baral. So I would like to invite Dr. Baral to give a presentation. Dr. Baral, the forum is yours, please.
Okay, thank you, Dr. Basanta. It's my great honor to receive your appreciation and then like encouraging words for me, and telling big words for me, saying that he's like a world-renowned scientist. To be frank, like I'm just on the learning phase, and like since 2015 to 2020, it's 5 years I'm doing research in geoscience, mainly in Central Himalaya, Eastern and Western Himalaya. Like frankly, it's called like throughout the Himalayan range. And my prime focus is on how the India-Asia collision took place and the analysis, the results is mainly based on the provenance analysis, shifting of the sediments from the source to the sink, and what are the mechanisms that influence the movement and the transportation of the sediment, and how it can interlink with the collision of the Indian plate and the Eurasian plate. So, shall I?
Yeah, please share your slide.
PPT?
Yeah, please share your slide. Yeah.
First, just give me a second. I'm very new in this Zoom. So.
Now just click the green
Share
button
screen.
at the bottom. Yeah, just click that.
It's coming?
It's coming, wait.
Okay.
Yeah, we can see. So you can make a full screen.
Yeah, now it's a full screen.
Yeah, we can see
it's
that.
Okay.
Please go on. Please go on.
Okay, I'm Upendra Baral, and then I'm from Nepal. I did master's from Trivandrum University, the world-renowned university from Nepal, in 2006-07. And after that, I moved my career from the earth science field to different part and work in different sectors for the administrative tasks in some other institution for 5 years. And then again, I'm back to geology and start my career as PhD scholars in key laboratory of continental collision and plateau uplift, Institute of Tibetan Plateau Research, Chinese Academy of Science. Like we can say the nature is beauty, and everyone loves the beauty. Everyone loves to see the beauty, study the beauty, and try to know in-depth knowledge about the beauty, how much, like how she is beautiful and how much she is beautiful. And to be frank, as an earth scientist, I like to say that the Himalaya is one of the beautiful and the most precious nature of gift from the nature to us. It's not going next. So, is it coming?
Yeah. It's coming, yes.
Yeah, is it okay?
It's okay, yeah.
Yeah, in China, like professor used to tell me that I'm like I speak quite fast. So if like I'm speaking quite fast, then please, you can stop me, okay?
Yeah, please go on. Now you are doing good.
Okay, so today, the prime topic about is the collision between Indian and Asian plate. Like when and where did it was collision? It's a big chain, like it forms 2,400 kilometer long mountain chains on the northern tip. That means the collision is not a pinpoint collision. There is the collision is accommodate the big area, big landmass. So, and there must be some like multiple thoughts about the different geoscientists when the collision took place and where the collision first time took place. So today I'm not like, to be frankly saying, I'm not that much of an expert to draw the conclusion till yet, but up to the knowledge that I gained from the time of my studies, I'm going to address, like point out when and where the first collision took place and how it's migrating, how it's shifting towards the east, west, or central part. At first, let's discuss about like where was the Indian plate during the late Jurassic time. During the late Jurassic, or before that, like before 160 MA, it was along with the landmass with the eastern and the western Gondwana. And then at that time, the Gondwana land started to move apart. And the big landmass, the Gondwana, start to separate to the western and eastern Gondwana, late Jurassic, sorry. And it later, the Indian plate separated from Antarctica and Australia along the southern Indian wrist and started to move and drift northward. And at late Cretaceous time, the India was almost moving and almost reached close to the Eurasian plate, and finally it get collided with the great landmass, the big landmass we call as the Eurasian plate, Asian plate at early Eocene time. So it's the big, it's not the, like today, the collision, the moment started and the next day there was a collision. It's the big time gap, like we can see like from 160 MA to 50 MA, around 110 MA, there is the gap, a big time gap from the initial time of rifting to the collision. So that's why the collisions should be properly addressed, and we must need to apply multiple technology, methodology to keep a proper collision age between the India and Eurasia. After this collision, the landmass that was deposited on the northern tip of the Indian plate, it forms the accretionary prism, and it was like moved and shifted to the like passive margin of the Indian plate, like just above the Indian mantle, and form the different Himalayan unit named as Cretaceous Himalaya, Higher Himalaya, Lesser Himalaya, and so on. So why, in a real scenario, every people used to say in a real field, what you are giving to the community, you are studying the rock and the collision. I don't understand, like, what is the importance of the collisions? Why you need to study the collisions? So it's like I used to say, the India-Eurasia collision is the most spectacular geologic event that found the past and the high Tibetan plateau. The Tibetan plateau start to rise at, get the elevation at 15 million years. So before that, it was a big landmass, and how it was uplifted, and what is the relation between the collision between Indian Asian plate and the upliftment of the Tibetan plateau. As well as the study of the collision is quite important to give the significance event, like what are the relations between Tibet and Central South Asia, and how the technically those areas are changing its like phenomenon, and what is the relation with the Tibetan collision between India and Asia, because the Indian plate is continuously moving northward, and it's pushing the Tibetan plateau. So that's why this pressure and we can say these tectonic activities each have some quite relation with the Central and the South Asian Asia tectonics. The initial collision is important not only for the how the Tibetan plateau form and what are the mechanism change, but it's also related with the continental lithospheric deformation, how the lithosphere deform, and after the collisions or prior to the collision, what was the change in the environment. And as I already mentioned, the Tibetan plateau already rise, and what is the paleo altitude reconstruction, and how we can reconstruct the paleo altitude, and why and how the elevation changes. And as I already mentioned, the collision is not only a single contact, because at the first collision, it starts with the soft collision, as we call the landmass deposited on the northern tip, or prior to that, the oceanic floor start to subduct, first collided with the Eurasian plate, and then after the complete subduction of that oceanic slab, there was a hard collision we call the continental collision between the Indian and Eurasian plates. So the collision started as a soft collision, and then finally it comes as a hard collision, and this is still ongoing process. That means the Indian plate is continuously moving northward, and then the collision is still going and accommodating the stress on the northern tip, or like we can say MST in the main Himalayan thrust, and that release on the form of earthquake and some other things. So as I already mentioned, the collision can't constrain by a single phenomenon or single study. So the important proxies that need to be done to constrain the collision are the migration of the plant and the animals. Like if there is a contact between the two continents, then there must be the movement of the animal or the plant from one continent to the another continent. And then if it start to rifted, then there must be some relation with the two continents. So we can relate the contact and the rifting and the suturing of the two continents together, and then like moving apart from like each other. as well as if there is the subduction of the lithospheric slab or even the continental crust, some of the like upper crust or the lower crust, especially the lower crust underneath the abducted plate, then it forms the magmatic rocks, especially the eclogite. And if we study this formation, the chemical characteristics of the eclogites, then we can get the proper age, like when it was subducted, and then when and we can relate it with the collision between two plates, either it's in India-Eurasia or any other part of the world. And when it start to collide, then the landmass which was deposited on the northern tip of the oceanic slab, like just above the oceanic slab of the Indian plate, we can say, like later we can say it's the Greater India, it exhume, it like uprise and then start to erode and deposit on the peripheral Foreland basin that was formed after the collision. So the geochronology, thermochronology, and some others like provenance analysis is strong evidence to constrain the collision between Indian and Eurasian plates. So if we combine some of these proxies, then we can properly constrain the collision between the two plates, India and Eurasian plate. Sorry. So as I already mentioned, the magmatic rocks that records the collision is like collision of the two plates. If one is subducted underneath the other plate, then obviously there must be a magmatic events on the active plate margin. So as we see, there are the numbers of the early stage of the early stage collision magmatic rocks in the Tethys Himalaya, which are really exposed on the Himalayan belt, like from Nanga Parbat to the Namche Babar, even in the Myanmar regions. And those magmatic rocks are like basically Oligocene to Miocene lithogranites and even the Middle Eocene granitic rocks. And the Middle Eocene granitic rocks are formed by the partial melting of the thickened lower crust. That means the crust was subducted underneath the Eurasian plate, and then later it moved upward, it come to the surface in the form of the magmatic rocks, and those are of Eocene age. And early stage of magmatism formed during the collision and subduction of the new, what's this yellow color is coming on the screen? I don't know, it's from me? Basanta?
Please go on, somebody has annotated, so you had to, yeah, please go on, it's okay.
At the early stage of magmatism, that means when the oceanic slab subducted at the first, then it's rolled back or it's tear off, and then it comes, at first it comes in the form of magmatic rocks, or we can say the arc, from the arc. And for an example, the Gangetic arc that was well exposed in Tibet is as a result of new Tethys slab subduction, and then later the continental crust, like lower crust subductions. So the new Tethys slab breakoff was almost synchronous with along the Indus-Sialung Sucha zone, which was the Middle Eocene age. That means the collision must be earlier than the 45 MA, because the collisions when the oceanic slab subducted and then it takes times to come to the surface. Like the magmatic rocks need some time to come to the surface as a eruption. So we can say the collision is earlier than 45 MA. However, some of the recent scientists used to say the collision is quite younger, and even it's some of the unpublished data I have seen that the collision is like 15 to 20 MA. So in our hypothesis, in our results, in our findings, we thought that the collision is at least not younger than 45 MA. Sometimes the screen is not coming down. So, as I already mentioned, the research progress regarding the ADS collision, there are a number of research has been done since the 1980s, or even say like early 90s. And basically those research are previously the research are only focused on one proxies, like one focus on the paleomagnetism, while next focus on the movement of like transportation of the sediments from source to the sink, and some emphasize on the formation of the foreland basins. So as we say, like multiple proxies need to be adapted to constrain the actual collision between, to give the proper collision edge between the Eurasian Asian plate. Like tectonostratigraphic response to the India-Asia collisions that forms the Tethys-Himalaya in early collision, like that deform the northern Tethys-Himalaya in the early collision stage, because it's on the northern tip and is close to the Indo-Sialung suture zones, and the sedimentary strata in the Tethys-Himalaya is quite like tremendously deformed as a resultant of the collisions. And the Iceland arc was formed on the northern tip of the like southern tip of the Asian plate and just north of the Tethys Himalaya. And there is, due to the increasing load of the accretionary prism on the northern tip of the Indian plate, there is a flexural load and it forms the peripheral foreland basin along the suture zone, the collision belt. And this peripheral foreland basins is a resultant of the collision, and they accommodate the sediments from the adjoining regions which was uprised due to the collision, uplifted and eroded, and finally it accommodate on the sediments which was uplifted, finally accommodate and settle at the peripheral foreland basin. So if we study the peripheral foreland basin sediment, then we can constrain the when the sediment were uplifted and and ultimately we can relate it with the collision between India and Eurasian plates. And those peripheral foreland basins are principally in the central sections. There are like developed between 65 to 60 ma. So the collision in the central sections, we can say, is nearly about 65 to 60 ma. And when they after the collisions and upliftment of uprising of landmass, then it forms the sedimentation mechanisms, the fluvial mechanisms from marine to the terrestrial. So it also indicates the collision between India and Eurasian plates. So, and especially in the Balakot section in the Western Himalaya, the transition from the marine to the terrestrial phases is recorded as 55 and 50 ma. So they constrain the collision in the Western syntaxis about 55 to 50 ma. And in Tibet, it's recorded as early Eocene time. But we need to emphasize that the deposition of the marine sediments will not have ended immediately after the onset of the collisions. So it's ongoing process. The collision started and it forms the like the basin, and the started to accommodate the sediments, but it's a long period of time they accommodate the sediments. Like we can say, for example, the Basin deformation, we can say it's almost like Eocene period. So it's the long gap, but it limits the first when the sediment was accommodated. That means it gives the first contact between the two continents. It gives the upper limit of the collision time between two continents. So if we study the foreland basin, peripheral foreland basin sediments, and then we can constrain only the upper bound of the collision time, but we can't limit like when it's closed or when it was ended. And the paleo latitude of the Greater India and Tethys Himalaya, like it means the Greater India started to move the sediment deposited in the northern tip of the Indian margin that call as the Greater India. We'll discuss this later as well. And it started to move. That means it changed the latitude from like southern hemisphere to the northern hemisphere. It passed the equator. That means, and we can, if we study this change in the latitudes from the time of deposition to the current period time, then we can say like how it's moving and what's its relation with the India-Asia collisions. Like as I already mentioned, the peripheral Foreland Basin have a typical signature about the signature to constitute the collision, and the well-studied section is the Sangdalin formations that's on the central Himalayan regions in Tibet. And that Sangdalin formation is Paleocene to Early-Eocene age, and the deposition environment recorded, like change in the deposition environment in this region was recorded at between 65 to 60 MA. That is the change from marine to terrestrial sedimentary environment at 63 to 65 to 60 MA. So being at all like mark the collision is in the central section must be 65 MA. And by the way, Tinglin is academician in the Institute of Tibetan Plateau Research, and he's my supervisor since the time of PhD, and till the date, I am working under his supervision and as a team member with his team. And later on, like Wu et al. Also mentioned that the collision in the central section is 60 to 65 MA. The paleolatitude, if I move the mouse, then I think you can see it clearly, yeah, Basanta? The Greater India, the sediment deposited on the northern tip of the Indian margin, it ultimately moved towards the north and finally collided with the Eurasian plate. So it's changed, like you can say 40 degree to 20 degrees south to, we can say 20, like more than 20 degree north. It's changed its paleolatitude. That means this about more than like 2,600 kilometer length of this Greater India. It's almost like remain close, and then it uplifted as a form of the Himalaya. That means it changed its route. It followed the route from this place to this place, and it changed the latitude from here to here. And if we deeply study like how it's changing its latitude from 40, for example, 40 to 35, 30, and then how it's changing its track, and then when it was like stopped, when the like movement, the change in the latitude is quite stopped, then we can say that the collision was in place, happened at that time. And in Tibet, it was recorded as like 75 MA and to 65 MA, and some other section in Chongpu formation, it was 63, and even younger at 65 MA. So from these results, we can say that these collisions must be like older than the collision in the eastern syntactic. Later we'll discuss about this as well. And sorry. And the geochronology, along with the paleomagnetic study, the recent studies by Yi et al. In 2011, it shows that in the western Lhasa, the collision happened, like it took place between 65 to 60 MA. So here we can say, like now in these results, it's the quite debate about the collision between Indian and Eurasian plate. It ranges from like 70 million years to the 35 million years. That means 35 million years gap between the collisions. Some study says it's 70, however, some says 35. So, and some researchers, well-renowned geoscientists says the collision took place in the western syntaxis, and some says it took place in the eastern syntaxis. Some says like it was the collision was on the central sections, and then later it was shifted to the northward, like eastward and southward. The vast majority, if we see in the Pakistan, the vast majority of the research say the collision took place between 55, even say like 52 to 45 MA, like the collision between India and Eurasian plate. And even the northwest India, it has somehow similar like age similar collision age between India and Eurasian plate to the Pakistan. But if you go to like southern Tibet, this was the quite older age, like 65, even 65 MA, and like the dominant age clustering between 60 to 55 and even some like 53 MA. However, if you go to the northern Tethys Himalaya, the age ranges from 65 and then the dominant are 60 MA. And if you further go to the Lhasa, is this quite similar age with the northern Tethys Himalaya and the south Tethys Himalaya. And if you further move to the eastern syntaxis, it's quite younger age, 45 MA and 55 MA. And our recent study also shows that the age is quite younger, that's 55 to 50 MA. So from this slide, from this data, we can say that it's the vast debate about the collision between India and Eurasian plates. Some says like it's a quite range from 70 to 35 MA. Some research says the collision took place at the central section at first, and then it like moved, spread toward the east and the westward, and the collision was first took place in the central portion of the northern tip of the Indian margin. It's 65 to 60 MA, and some says like it was 55 MA, and some even says like 55 to 56, and even Atkinson and the team, they says like 30, the collision between India and Eurasia is quite young, 30 to 25 MA, and this collision was not the actual collision between Eurasian and Indian plate. They say that is the collision between the some portion of the Himalayan unit with the Tibetan plateau. And ultimately, whenever the collision and wherever the collision took place, it formed the Himalayan belt, like 2,400 kilometer long Himalayan belt, which is quite exposed, well exposed from Khoistan to the Namche Barwar, from Pakistan to the India, northern India. And it divided, like we can say that the mountain chains that forms due to the collisions between India and Eurasian plates are separated into like principally four little units: Tethys Himalaya at the northern tip, and higher Himalaya, which is composed of high-grade crystalline rocks and inclusion of some granitic rocks; lesser Himalaya, which is metasedimentary sequence and quite older age; and the youngest unit, the sub-Himalaya, it's called the Shivalik, and it's fluvial unit which was deposited in the middle Miocene to early Pleistocene. And recently the quaternary deposit, those are like well exposed in the northern, in the south of the main frontal thrust. And if we study, like for example, for me, I'm working on the provenance analysis. So first, before that, I must need to know what are the age of those Himalayan units which are the prime source of the detritus in the foreland basins. So if we principally say, like if we see the Tethys Himalaya and the higher Himalaya share the quite similar age patterns, but the lower lesser Himalaya is quite distinct. They are dominantly peaked around 1.7 to 2 GA, like 1500, like 1700 million years to 2000 million years. The dominant detritus, the detrital zircons in the lesser Himalaya were peaked around 1.7 to 2 GA. Whereas the higher Himalaya, the sediments are dominantly peaked from 800 to 1200. The cluster dominantly cluster between 800 to 1200 and peak at 150 to 1100 million years. The difference between Tethys and the higher Himalaya is that in Tethys Himalaya, especially, there is the peak is about 500 million years. The detrital zircons dominantly peak at 500 million years. So while comparing the age with the sink and the source, the prime focus need to be given about the peak, dominant peak. that's quite relate with the source and the sink that I did on my research. So let's say, like, first the sediments exhume, the sediments exhume at the source, and the different mechanisms, the fluvial systems, the glacier, the wind, whatever the mechanism, they transport the sediments from source to the sink, and finally they deposit it in the basin, and the basin in the peripheral foreland basins and the strata. And if we study properly the sediments, the mechanisms, the phenomenon, the structure, the compositions, the sediments of all the sediments that deposited in the basin, then we can track back the source regions, and finally we can relate it when the sediments in the source started to erode, and then what transport the sediments from source to the sink and how it was deposited. So principally the provenance analysis research is focused on this phenomenon. And in the Himalayan regions, the peripheral foreland basin regions on the southern slope of the Himalaya, the sediments deposited before, like 42 million years, those are in the marine environment. And after that, there was a huge depositional gap, and the sediments, the fluvial system changed to the like alluvial, or we can say terrestrial sedimentations. So it must happen, the collisions must be somehow older, and then there must be some gap after the collision, and the fluvial systems change as a terrestrial from marine to terrestrial. The deposition environment changed from marine to alluvial. So the collision must not be younger than 42 million years. And if you see the Diesel's 2004 paper, he says that this Amile formations, it's the Paleocene to Upper Cretaceous to Paleocene like sediments, that there is lack of the sediments younger than almost 1500 MA. That means there is lack of sediment. The source is not there. We can say there is not any source of the sediments that contains the ZIRCONs, which are quite younger than the 1500 MAs. If you come to the Moisekati formations, there is the dominant number of the grains. There we can see the peak of the detritus, there are 500 MA. That means this sediment must be sourced from the Tethys Himalaya, and prior to the deposition of the Moisekati formation, the exhumation of the Tethys Himalaya was not in place. That means the collision was not in place that uprise the Himalayan unit. So we can say the collision must be somehow between the deposition of the Amile formation and the Moisekati formations. And afterward, there's the continuous, the source of the sediments, we can say the mechanisms, the distribution of the detritus is quite similar. And prior to the collisions, there's quite similar is distribution, which dominantly peak around 1700 to 2000 million years. So this is quite similar to the lesser Himalaya. That means this must be shown, the sediments must be sourced from the Indian Craton. That means the southerly source sediments, and from the time of the Moisekati deposition of the Moisekati formations, there is a mix of sediments from the southerly slope and the northerly Himalayan units. So we can say the collision took place after the deposition of the Amile formation and at the time of the early stage of the deposition of the Moisekati formations. And this change in the provenance is quite helpful to constrain the collision age between the continents. Okay, let's discuss some about the phenomenon, the lithological descriptions about those units. The Amile formations, it's quite 230 meter thick and typical in typical locality. It's green to gray color calcareous sandstones with some cells, which is overlain by the Moisekati formations. It's quite dominated by the thick shale deposit with some limestone lanes and fossil ferrous-nummulitic fossils. It's indicating the Eocene age. And later on, the Dumri Formation is the first fluvial sediment deposited in the Foreland basins. Especially, we can say Omile is not the Foreland basins, and Omile and Boinsekati Formation is peripheral marine deposits, and some part of the Boinsekati and the Dumri Formation are deposited at the fluvial environment on the southern slope of the Himalayan belt. And in my study, like same as the Diesels and his group, we can say the Omile Formation, the sediments are quite dominant, peak at 1700 to 2000 million years, whereas the Boinsekati and the Dumri Formations there are quite dominant number of the grains resembling the age of the higher Himalaya and the Tethys Himalaya. So that means there is some change in the source between the deposition of the Omile and the Boinsekati formations. And that's why we say that the Omile formations dominantly sediments were Indian affinity sedimentations, which are the same mechanism as the Sangdalin formation in the Tibet. And in Sangdalin formation, we can see some very few number of the gangetic sediments possibly is the close to the source regions that was, and this arc was from the Tethyan slab subductions. And later on, Boinsekati formations, there is the mix of the sediment source from the accretionary prisms that the Himalayan unit, the current Himalayan unit, which exhumed after the collision, the hard collision between Indian and Eurasian plate. And later, the Foreland Basin is start to migrate southward, and it deposited the Dumri formations. And at these times, the Himalayas was already raised, and there is not any source of the sediments from the southern slope, and only there is the source of the northern Himalayan unit. So the Dumri formations are mainly source, we can say only source from the Tethys Himalaya, higher Himalaya, and the lesser Himalaya that was that well exposed on the northern Himalayan belt. And if you want to read more about this, and then you can find in my paper that was published in 2018. Not only the UPB age, if you go through the Hafnium isotopic age, then you can say the Omile formations, the Hafnium isotopic value are quite positive. Dominant number of the Hafnium isotopic results, it's dominated between 0 to 10. That's indicate this the source is Jubilant cross. That must be Indian cartoon. And after that, if you go to the Boinsekati formation, you can see this the dominant like white exposure, like the wide distributions ranging from -30 to 20, even -40. So it's a mix of sediment, the detritus, the Hafnium isotopic is distribution from positive to the negative resembles. That's it suggests the orogenic belts both from like the Jubilant crust and the exhumed Himalayan unit, and it's quite similar to the Dumri formation. So there must be the change in the source regions from the from the time of deposition of the Omile formations to the Boinsekati formation. So we mark this line, the change in the sedimentation as the collision between India and Eurasian plate. And along with this, not only this is, but we took the biomarkers, we can say the biostratigraphic study that constrained the age of the Boinsekati formation as the Eocene, and like all those we can say like the grain size distributions, the thermochronological data, and some of those findings. So not only one proxies, we add up, we took the results, we review the results from the published data and along with our current findings, and we conclude the collision between the India and Eurasian plate, especially in the central Himalaya. It was happened between the time of deposition of the Omile and the Boinsekati formation. And let's talk about some younger strata. That's the Siwalik, which was deposited between middle Miocene to early Pleistocene time, and it's dominantly the lower part is mudstone with variegated mudstones, and that was followed by the coarse grained sandstones with very few mudstones, and at the top of this middle Siwalik that was marked as 5.2 to 4.2 million years. There was a change in the fluvial systems from meandering to the thick bedded and meandering to, it is the fluvial system changed to the meandering, and then it deposited the very coarse grain conglomerate at the top or upper part of the strata that calls at the upper Siwalik. And if you follow the details paper in 2004, then you can say in the Dumri formation, Eocene Boiseka deformation, the and the isotopes, it was quite negative. And then after that, it was constant at the time of Dumri formations. That means from the time of Boiseka deformations, it was changed. The sediment source is quite changed. This is dominantly from the Himalayan unit, whereas it's a mix from the Himalaya as well as Indian cartoon. So it was changed, and then it was somehow constant, showing the positive results. That means there is a change in the sediment source and the fluvial environment change. So somehow the collision must not be younger than the deposition of the Boiseka deformations. And in Siwalik also there is change. There is change in the pattern, the distribution pattern of the DETRITAL ZIRCON, or in the middle Siwalik we can see dominantly like the Cenozoic grains in the Western Himalaya. There is much more eroded leucogranites. There we can see some younger grain of that. Quite similar to the leucogranites is, whereas in the western part it's quite different. And after 10 million years after the deposition of the lower Siwalik, and it's the time of deposition of the middle Siwalik, there is dominant number of the grains resembling the ease of the lesser Himalaya. That means the lesser Himalayan duplex was started to form at 10 million years, and it started to erode and deposited at the Foreland basins that we can say as the Siwalik. And if we go east, further east, at the eastern Himalayan syntaxis, we can see, we can see that the similar pattern of the age distributions that was recorded in the western part, and it's quite younger that was published in our research in the central sections, which was about 65 to 60, even like some older 70 to 68 million years. But if you go in the east, there's also change in the deposition environment from marine to the fluvial environment, marine to the terrestrial environment, and you can see there's change in the pattern of the deposition distribution of the DETRITAL grain. If you see the lower Inkyong formations, which was like early to middle Eocene, middle to the upper Cretaceous, lower Eocene, there is absence of the younger DETRITALs like than 500 MA, whereas the early to mid Eocene strata, the upper Inkyong formations, we can see the number of the grains, like 134 grains out of 471 grains are younger than 200 MAs. So that means there must be change in the deposition environment. There must be in place of some tectonic activities between the time of deposition of the lower and the lower and the upper Inkyong formations, which could be the collision between the India and the Eurasian plate in the eastern syntaxis. So the results constrain that the India-Asia collision in the Siang Valley, that means northeast India, south of the Namche, it took place during or before the early Eocene time. And the paper was published in 2019, so you can follow the paper. If you go to the fourth, in the Western syntaxis is the same, like the Potala formations, it's similar to the Amile formations, which was deposited in late Paleocene between 57 to 55 million years, and it's rest over the Margala formations with the disconformable contact, and it contains the nodular limestone, the Kundala formation, the Kundana formation, and the Margala formations are marine deposits, whereas the Mure formation is quite similar with the Dumri formations in the central Himalayan sections, and it was deposited in between the during the early Eocene times, same as the Dumri formations in the central Himalaya. And if we see the age distribution pattern in this section, in the Western sections, we can see there is similar to the central and the eastern sections from our study. There is also change in sediment, the distribution of the detrital zircons. Here in the Potala formations, there is absence of the younger grains, whereas in those like this Kundana and the Muri formations, there is quite younger grains. And this it says that like 55 to 56 billion years, there must be change in the source regions.
Dr. Bora, we are seeing the screen where you are showing the Eastern Himalayan Cenozoic Foreland Basin of geological map. Are you showing the same slide, or there is some problem with the slide changing?
No. I already moved. So
so that's why. Can you just click out once and then put it again? Because we are
can I stop and then reshare again? You mean?
Yeah. Please.
Okay.
Yeah, please share it again.
Thank you for your notation, Dr. Basanta. Where is my slide? Oh, sorry, there's some problem, might be.
Yeah, I know it happens sometimes.
So if my time is going to over, then just you can stop me, okay?
Yeah. Just
you mean you just get this slide, and after that it was paused, no?
We are not receiving your slide till now. Please share your slide.
Share screen.
Yeah.
Where is it? You need to PPT. I don't know why it's not sharing.
Yeah, it's coming. Wait.
It's coming?
It's coming.
Okay,
yeah.
Thank you. Okay, then I'll just take a quick look.
Yeah.
And as I already mentioned, well, it's not. And the eastern syntaxis is there is a change in the distribution pattern of the detritus in the Foreland basins between the lower Inkyong and the upper Inkyong formations, same as the Amile and the Boinsikati formation in the central sections. So we mark this change in the sediment source as the collision between the Indian and the Eurasian plate in the eastern syntaxis, which was in place, which took place between during or before the early Eocene time. That means deposition prior to the deposition of the upper Inkyong formation. And you can find this paper in 2019. And same in the Western syntaxis, there is a Potala formation. It's quite similar to the Amile formation and Margala hills and the Kuldana formations. It's similar to the Boinsikati formations, and the Muri formations similar to the Miocene, early Miocene Dumri formation in the central Himalaya. And if you go through the age distribution pattern in this section also, you can see there is a change. There is a missing of the younger grains in those Patala formations, whereas in Margala hills and Kundala formation, and even in the Muri formations, there are dominant number of the grains of like we can say Paleozoic grains, even the Cenozoic grains. So there must be change in the sediment source between this deposition between the Patala and the Margala hills. So in these sections, our study marked that the collisions must be 56 to 55 MA, that is the time between the deposition of the Patala formations and the Modi formations. And if we see the tectonic activities, how is it changing, means at 140 to 65 MA, there was the oceanic slab in between the Indian, you can say Lhasa and the Indian plate, and it's the Tethyan Ocean slab was continuously subducting, and then later at 55 to 53 MA, prior to 55 to 53 MA, it was completely, the oceanic slab completely subducted, and then there was, and we can say this is the soft collision, and then it took the hard collisions and it exhumed the sediment deposited on the northern tip at the Tethyan Oceans, and it uprise, it exhumed the sediments and formed the accretionary prisms, and the sediments start to erode and then deposited in the peripheral foreland basins. And the basins migrated, we can say the first peripheral foreland basin was close to the Indus-Yarlung zone, the collision zones, whereas the later on the younger sediment basins, it start to migrate towards the farther from the suture zones towards the subducting plate. And this is due to the flexural load after the erosion and the accommodation of the sediments. And the paper was published in 2018 in EPSL, and then you can follow this paper for detail if you want to get some insight. On these findings, there are so many studies, and then it's limited time, I can incorporate all those studies, but with the, this number of studies, there are tremendous studies that have been done in this collision belt, especially in the central sections in the Nepal, Himalaya, as well as the western and the eastern syntaxis. But especially in the eastern syntaxis is less studied than the western and the central Himalaya. But however, the number of the studies, based on the number of the studies, we can say that the collision was first took place in the central sections, we can say, and that formed at the Nepal Himalaya sections, and then later on it migrated, the collision migrated, took place on the western and the eastern syntaxis. The provenance and the change of the depositional environment in the foreland basin could be the result of the collision between India and the Eurasian plate. As I already mentioned, if we study the foreland basin sediments, there is change of the sediment environment from marine to the terrestrial, and the source distribution pattern of the DETRITAL ZIRCON is different. The lithological compositions is quite different, as we see in the Amile formation is dominant of the sandstones, whereas in the Baisakari formations, it's dominant by the shale and limestone. So the composition, lithological composition is quite distinguishedly different between these two units. Along with all the thermochronological data and some others, numerous paleomagnetic data, we constant that the first India-Asia collision took place in the western syntax, like before 55 to 50 MA in the eastern Himalaya, whereas in the central sections, it was 65 to 60 MA, even some older 68 MA in the central sections, and it's in the eastern syntaxis. It's quite younger, but it's than the central Himalaya, whereas it's quite similar to the western syntaxis, that's 55 to 52 MA. So the first initial contact between India and the Eurasian plate took place in the central sections, and then later it was collided with the eastern and the western sections. And as I already mentioned, the India-Asia collision took place in the central Himalaya and later migrated towards east and the western syntaxis. I have published a number of the research, and this has the quite in well-renowned journals. You can follow me in the Google or in ResearchGate, in other some like academic portal, and then you can download the paper. And if you don't have access to the paper, then if you don't have a budget from a lab, then you can request me, and then I can help you to get those papers for the early career young scientists which are from the developing country. It's not quite ethical to say, but for the young scholars which are from the underdeveloping country, even developing countries, they don't have access to the paper, download the paper, then you can send me an email, or you can text me by mobile or any other media and electronic media, then I can send you the paper. And I'm then more than happy to facilitate, to share the knowledge, whatever I gain during my study until the date. And last, thank you for your attention, and hope I'm able to share some of the findings about the India-Asia collision, the controversies that was still remain when the India-Asia collision took place, and where the first contact between the Indian and the Eurasian collisions took place. And the research is still going, and still I'm also learning phase, like, and till the date I can't draw the proper conclusion, but based on the findings that I conclude, the collision was first took place in the central sections and later on the eastern and the western syntaxes. And at last, I'd like to thank Professor Pinglin, the key laboratory of continental collision Tibetan Plateau, that give me the platform to do this research, and the IHRD to get the platform to share my knowledge to all scientists in this remote access platform using the advanced technology, and the Suros who is facilitating this program, and Dr. Basanta and all the listeners. Thank you all. And I'll be more than happy to answer the comments, your suggestions, and your all the things. If you want to mention, if you want to ask, then you can freely ask. Yes, thank you very much for your time and your patience. Thank you, Dhanyavad. And especially at last, I'd like to say, for the Nepalese scholars, please do research. And then if you want to do research, and if you don't have access to the paper, if you are facing problems to do the research, to write up, start to write up. All the young scholars, please start to write up. And if you have any problem, then I'm sure Dr. Basanta will be also more than happy to facilitate you to improve your writing, to give some idea, to share his knowledge. And then I'm also more than happy to facilitate you to share my idea, and then like to bring your paper, to bring your writing to a paper, to transform your writing to a paper. And then please do research, start to write, and start to publish. Thank you, Basanta. Thank you, everyone.
Thank you, Dr. Boral. It's a wonderful presentation. So can you close your slide sharing?
Okay.
Yes, thank you. It's a very interesting and insightful presentation about the geological studies about the India-Eurasia collision, because it's a hanging discussion, as you have rightly mentioned. And yeah, we know that your research is mostly based on this provenance analysis. There are lots of things like paleogeography or magneto and others, and other things that people are doing research from around the globe about this collision. And there are lots of questions, and there are lots of unanswered questions. And I'm pretty much sure that your research experience and your expertise and your results have been already indicating some of the limelight towards the understanding of Indian and Eurasian plate collision. So I'm pretty much sure that I can see there are lots of colleagues from around the globe, and they must have some interesting questions both in Facebook and in Zoom chat box. But let me start from myself, and then we'll jump to the audience. Dr. Boral, it's very interesting, to see lots of your interesting data from Eastern syntaxis to Western syntaxis relating these younger rocks. Even you touched upon these Eocene sediments in Brinscati, and there are lots of the discussion going on about the lesser Himalaya, higher Himalaya, and then the provenience to the Shivaliks, starting from Potwar Basin to the Eastern Himalaya. So in your provenience analysis, because some of the researchers, they have indicated that, the slab was break off, and then some researchers are saying that there was another, not plate, but kind of some, lithospheric something between Indian plate and Eurasian plate, and then it collided differently. So there are the different pattern of provenance distribution in the Himalayas. And some of the researchers, they believe that, the Indian plate first collided in the eastern side, in the eastern syntaxis, and then counterclock rotation, and then it took near about 10 million years so to reach to the, juxtapose in the, eastern syntaxis. So how you take this debate, or how you synthesize or modeled this kind of others argument with your research from the provenance analysis basis?
Okay, thank you, Basanta, and first, thank you all for listening me. As I already mentioned, like if you just follow one proxy, for example, the paleomagnetic studies, then it gives the different idea, like not the we can say, if you follow the only one track, then it gives you the result. It enlightens you on only on the one track. And if you compile your data with the previous results, or if you do the multiple analysis, use the multiple proxies, then you can surely say when the plate is movement, and then how it's movement, how it's collided, and how it changed the deposition environment, the mechanisms that took place after the collision between India and Eurasian plate or any other plate subductions. And yeah, as you mentioned that the slab is rolled back or it's moving parallel to the mantle, then to be frankly saying that I don't have that much of in-depth knowledge about the rollback, because I'm dealing with the provenance and the change in the provenance. So I think it's not strong enough for me to put my words idea on that things till the date. So I'm frankly saying I have to say sorry about the rollback, because but some studies have shown that the lithospheric slab underneath the Indian continent, Indian landmass, we can say like India, it's rolled back and it tear, and then it's amalgamated, and it mixed with the mantle and come as the source, as the magma in the northern tip, or even the southern tip of the Asian margin. For example, we can say Loite batholith, like Kohistan Ladakh arc, and Gangetic batholith, and the phenomenon, the geochemical characteristics, and the age distribution of those magmatic rocks is still on debate. Like some researchers shows that it's from mantle source, and some says it's mixed up with those Indian continent landmass, and then it comes to the surface at a different time. First, it was the Indian slab was subducted, and then it comes somehow the upper part, and later when there was hard collisions, and then it again amalgamated, mix up, and then it comes to the surface. So it still is debate, and then there is quite controversy about how is the role the subducting Indian slab is subducting underneath those Indian plate. Sorry, Asian plate.
Thank you.
I answered your questions.
Yeah, I mean, it's a long-hanging discussion. I just wanted to know your view,
Yeah.
Okay, I'll take some questions. So I can see the Ajay Rautela. So his first question is, when Indian and Eurasian plate collided? I think you have already explained that. So the another question is, how can we identify thrust in the field, and how to identify that if there are any tectonic activities or in area. So he's trying to ask, how can you identify thrust and fault in the field, and if there are some new tectonic activities are existing or going on there?
Like as I mentioned there, the principal signature is the change in the depositional environment from terrestrial to marine or marine to terrestrial. There is you can find there is some change, proper change of the environment, and if you relate that with the biomarker, that means the migration of the animal and plant from one continent to another continent, then it will be much more helpful for you to mark. But only from the field observation data, if you find there is some like volcanic ash layer in between two strata, then you can easily mark there must be some magmatic activities as a resultant of the collision, and it deposited on the ocean floor. And after that, that was a collision. So there are multiple proxies you need to relate in the field to mark the change in, like mark the boundary line, that is, this was sourced from this region and the next is sourced from the next region, and there is some tectonic activities that happen in between those two depositional environment, the time of deposition of two different strata. But not only from the field observation data, it's very hard for you to do it, but you can use the structure, the microstructure, the macroscopic, megascopic structure in the field, that the overturn fold, the large scale fold, fault, and thrust, those change, like drastic change, it might be helpful for you to mark. But not only the field data is quite enough to say this, the change, like the collision between this any continent.
Yeah, but that's a wonderful answer. And if you want to see some thrust and fault identification within the small area, for example, in the Himalayas, there are lots of methods that Dr. Baral has already explained, and you can analyze the geomorphological changes with some other properties that you can do research on aerial photo and others. Thank you, Dr. Baral. So there's another question from Akshay Outkasi. So he's asking, or she, I don't know, can you give more insight on the nature of provenance of ink-kong formation and its correlative formation in the Western syntaxis?
You mean like ink-kong formation, the lower ink-kong formations, if we see the lithological composition and the age distribution pattern, then it's quite similar to the Amile formations, and we can say the Patala formation in the Western syntaxis. In the Amile formation in the central and the Patala formation in the Western syntaxis. So, and if you do like the detailed age distribution, the morphological characteristics of the ZIRCON, then it's quite similar to the Patala in the Western syntaxis.
Okay, again, I will continue his question. So can we expect any petroleum system presence in Western and Eastern syntaxis, piggyback basin or intervalley basin in your experience?
Yeah, here also, frankly speaking, like there must be some, if it's deposited in the marine environment, then in my, as based on my knowledge, there must be some reserve of some petroleum, like the natural biogas, we can say, some others fuel in between those strata, like the upper strata, for example, the Dumri and the Siwalik, they might act as a cap for those reservoir, and there might be deposit. There might be a reservoir of the petroleum in Waisakati formations.
Okay, thank you. So another question from Rui Lee. So how do you think the GIB model, do you think there is any geological evidences for that and relating with geophysical model?
Sorry, I didn't get it.
So really is asking, how do you think the GIB model, I don't know what does it mean, GIB, do you think there is any geological and geological evidences for modeling? Something like that?
Yeah,
Really?
might be, if I'm not wrong, she used to ask like, yeah, how I can say like the existence of the Greater India Basin models. It was first
Yes.
proposed by, and
Yeah, yeah.
it as there must be some like sedimentary basins that accommodate the sediments from the southern source and from the other region, Antarctica, Australia, like Nibua, those regions, the sediments were transported and accommodated on the northern tip of the India prior to the collisions with the Asian plate. That is called as the Greater India Basin. It's more than 2,600 kilometer long basin. And later on, if we see the shortening of the Himalaya, if we talk about the exhumation and the formations, the uprising of the Himalaya, the Cretaceous Himalaya, and that the basin, the sediment deposited on that Greater India Basin, it was uplifted and formed the Himalaya at the present form. So the shortening of those, the accommodating of those Greater India Basins ultimately form the Himalayan regions. So I'm on the point that there must be the existence of the Greater India Basins that accommodate, that deposited the Himalayan unit on it.
Okay, thank you. So Krishna Kumar Singh is asking, and it's a huge debate and is still now. So is the height of Himalaya is increasing? Then if yes, how much high it will be next, let's say, year or so?
It's like if you see, if it's the subduction is continuous process, that means the Himalaya must rise, and it says like 2 centimeter per, like 2 millimeter, I guess, per year, or 2 centimeter. I forget it at the present. It's uprising, but at the same time, the erosion process is also undergoing. The fluvial environment, it's continuously eroding the Himalayan unit. So the uprising and the erosion process is both undergoing. So that's why we can see, like from today, like this year, the Himalayas was, we can say Mount Everest is rising next year by 2 centimeter, next year by 2 centimeter, next year. But its erosion process is still undergoing. So I can say, I'm assured that the uprising, the height is increasing, but the erosion is also undergoing. So it's to and fro, it's going up, going down. So
Yeah, I mean, this is very important question to understand, because, when you talk about the upliftment of Himalaya, then we have to discuss that with the denudation. There are lots of geological processes that acting upon the Himalayas. So we have to understand the upliftment and denudation. So there are lots of studies going on, and it's still very early to say that how it will go in days to come. But I agree with Dr. Baral that we have to think on that way. So another question from Naren Adhikari. So he's writing that nice presentation. So based on your study, what is the provenance of Neolithic limestone bed of Bhainskati Formation?
as I already mentioned, the Bhainskati Formation is sourced from the Indian cartoon, and we can see like some younger grains that is quite similar with the Tethys Himalaya. So, and higher Himalaya. So it's a mix of the source from the uprising Himalaya as well as the Indian cartoon. But so that's why prior to the deposition of, and the early stage of deposition of the Bhainskati formations, there was a collision and it changed.
So thank you, Dr. Baral. So I'll take one question from Dr. Diliram Thapa. Just can you ask the question very short, direct to the presenter?
Yes, sir.
Dr. Thapa? Yes, please.
Yes. Thank you, Dr. Baral, for your informative presentation. Today, I really enjoyed this webinar. And my query is that how is the age of the Himalayan leucogranite are related to STDs or MCT? Could you please elaborate more on this?
Okay, and like the leucogranites are quite similar with the age of the MCT, main central thrust, which was like 25 to, you can say 20 and even 12 MA. And so that's why I think that the emplacement, the eruption, the formation of the leucogranites in the Himalayan unit is quite interlinked, relate with the activation of the main central thrust. And the STDS is the normal fault. So, and I don't think that the STDS play a key role to the formation of this leucogranites in the Himalayan region.
So thank you. So there is another question from Ujjal Sharma Timsina. Although Krishna Kumar has given some answer, but the question is, so is it possible that Indian plate gets completely subducted to the Eurasian plate?
Yeah.
Because it is subducting 2 centimeters per
I read
year.
the question.
Yeah,
usually, like for earth scientists, it's quite interesting to say that 2,500 million years ago, we are on the southern hemisphere. The land mass is in the southern hemisphere. And after 2,500 million years, again, we will move to the southern hemisphere. So if this mechanism is ongoing and if the collision is ongoing process, and if then obviously one day the Indian plate is completely subducted or it's tear as a part of some microcontinent and then start to rift it as from Asian plate, and the process of complete subduction of the Indian plate, and it won't be the existence of the Indian plate in future. But it's not happening tomorrow or like the next year, or my grandson will see it. It must take like more than 100 or 200 million years, and we can't predict that much. But if you see the history, then it might get happen. But not only the whole Indian plate gets subducted, but some portion it will get subducted, and then some part it might get tear, like from MCT, from other thrusting system that already existed in the Himalaya, that might play a rifting for those like Indian plate into the too many microcontinent in near future. Like Madagascar, it's tear from the Indian Cartoon, and like Sri Lanka, it tear from the Indian Cartoon. So it might get possible that Indian plate will get smaller, and then there might be chances of the existence of the Indian plate in near future. This is my thought, my understanding.
Yeah. There is still huge discussion going, and some of the scientists, they don't, not completely disagree, but they have different opinion. What you have excellently presented.
That's why science is a debate.
Yeah, I request a participant, if you have any question, please write within 5 minutes. Then after we'll close the chat room, and then we will not able to address any question. So I would like to request
if you have any queries, then you can write me by email.
Yeah. So there is another question from Ashish Mishra that I have explained, talked before also. So he's asking that is various Himalayan landforms were formed during the collision of plates, or they were formed later due to the climate change and other activities in the Himalayas?
Yeah, not only the collisions play a key role of the change in the sedimentation and like deposition of the sediments and formation of the rock. There are multiple proxies. If there is a collision, that means it ultimately changes the climate, the environment, the surroundings, everything over it. And it's within if the collision took place today, then in between like upcoming 10 to 15 million years, there is change in the distribution of the the plant animal distributions, the existence of the plant and animals, and the environment. The precipitation mechanism will change, the temperature variation will be changed, like the glacier, we can say the temperature will be coolest to form the glacier, and humid and dry. So it's multiple proxies will happen in between the time of the collisions. So there are various proxies need to be
Yeah.
addressed, and then we can follow. There will be happen the various mechanism, various things will happen at the time of the collisions.
Yes, thank you. Thank you for your short answer. There's another question from Siva Prasad Mohanty. So asking, from the basic knowledge, we know that only oceanic place is subducted due to its density, but how could it be possible for a continental plate to subduct? What's the reason behind it? Do you have any insight on that, Dr.
The
Bora?
continental crust is dense than the oceanic crust, and when the oceanic crust start to subduct, if we say for in the first slide I saw that the two cars collided each other, and the heavy and the dense car it's get read like stead, and the light won't move, like it changes its velocity. And as we see the oceanic crust, it was quite heavy, and then it subducted underneath the Asian plate, and later on maybe it was continuously follow the track, and the lower crust of the Indian continent, it followed the track from the oceanic slab, and then it subducted underneath the Eurasian plate.
Yeah, thank you, Dr. Boral. And I think I'm receiving the last but not least question. So from Binayak Pant. So asking what are the, I don't know, is your area or not, what are the reasons for the mud eruption from the seabed at the shore of Chabahar?
To be frankly speaking, I don't have much more knowledge, but based on my studies, the mud flow could be, it must not come underneath the lower crust, because the mud, it can't unseat. If you follow the crust, it's dense, and it composes dominantly the hard rock. So that's why it must be from the upper crust part, and there must be some local thrust or local fault systems that circulate, that move, that act, that mud part, that mix up with it and make it viscous, and then it comes to the surface like a volcano, it comes. So in my opinion, in my little knowledge, it must be from the lower, the upper crust, some portion, maybe we can say not more than 1 or 2 kilometer depth, and then it must circulate as a form of the viscous material.
Thank you, Dr. Bola. I think I'm taking the last question. So from Province Rest asking, there are lots of, temperature changes in the subducting plates. So in your opinion, do you have any insight on which part the most of the subducting or the energies are considered to be concentrated?
When the slab is subducted and then it reaches to the lower crust, or is reached to the mantle, or even the lower mantle, then we can, it gets the temperature. It's already, the mantle already have immense temperature and then immense pressure. And then if the oceanic slab or the subducting slab is mixed with the mantle, then it adds some more pressure and temperature on it, and then it forms we can say the ultra high temperature and pressure rocks as an eclogite, which are seen on the active tectonic collision margin. But interestingly, we can't see eclogite on the Nepal Himalaya. Might be is the lack, it was what we can say, it was covered by the Himalayan axiom Himalayan unit, or it may not, it's not compulsory that the eclogite should form, and the amalgamated, the mixed crust mantle part should come to the surface. It might be consolidated underneath the surface. So, but in the eastern and the western syntaxes, we can see the eclogite, which are formed due to the, which are showing the immense ultra high temperature and the pressures that only forms in the active continental collision zones in the mantle region. So I guess I answer your questions.
Yeah, Thank you, Dr. Boral, for your marvelous presentation and very good Q&A session, and very pleased to know your vast experience on this Himalayan region, on this geoscience. And then thank you very much for your presenting your the studies and your papers, and then summarizing all these things. I think we have we have understood some of the fundamental principles and the fundamental challenges that we are facing in the Himalayan region. So this is the primary objectives of this webinar series. And the first is Dr. Boral today. And thank you very much, Dr. Boral, once again. So I will share another slide. So can you see my slide now?
Not yet. Basanta Adhikari study screen. Maybe it takes time.
It's coming, right?
Yes, it's visible.
Yes. So so next Sunday on 2nd August, Professor Alexander Webb from University of Hong Kong is going to deliver his talk on how mantle dynamics guided the main phases of Himalayan crustal tectonics. This is another study which linked with the Dr. Boral, what he has presented rightly today. And next Sunday we'll discuss more on, but the time is 7 p.m. Nepal time, 1 hour before today because of the time difference between Nepal and Hong Kong. And IHRR will post this poster and the registration link in their social networking site. And I think you all registered participant will get the email and with the presentation of Dr. Boral, an invitation to join the Dr. Webb presentation next week. So of course, everybody will get a registration link. So thank you very much, IHRR, for providing me opportunity to moderate my esteemed colleague, Dr. Boral. And I'm always pleased to be with him, especially in the field. I always, enjoy during the work and, walking like 10 hours or 12 hours a day from, 1,000-meter elevation to, 3,000 meter in a single day. And, it's like a journey, that's why, I cannot say it's expedition, but, it's a journey to work on this, geological studies in the Himalayas, not only in the Nepal Himalaya, but from western to eastern syntaxis and central Himalaya. So we are working with Dr. Boral, working on these, how we can use this geological, information for sustainable, disaster risk reduction in the Himalayas, especially in the earthquake and then the landslides and other natural hazards that are, we are facing in the Himalayan region, starting from western to eastern part. So thank you, Dr. Boral, once again. And
thank you. Thank you very much for giving me a chance
you.
to share my idea. Like I see the Mary is smiling, so that means like I'm able to share the knowledge, whatever I had.
Yeah. She joined lately, but I can see her. Yes, of course, someday she will put in some of our insight in the, Everest region. We'll ask her also to give a presentation in days to come. And thank you, Dr. Boral. So I would like to request to Suraj Gautam to end the meeting.
Thank you so much. Thank you so much, Dr. Upendra Boral, for the wonderful insights on where and where did the India-Eurasia collision take place. The session was purely technical and was really informative. It was really good to know about the collision patterns and so many things. We'd also like to thank Dr. Basanta Adhikari for his excellent moderation and making this webinar environment more lively. It is always a pleasure hearing from you. I believe this session has definitely added important insights to our understanding and has also been very helpful to all our participants. The Q&A session was also really interactive with a number of questions. We had some interesting questions like regarding the collisions, subduction phenomenon, and even the identification of thrust in the fields and so on. So I think, yes, we tried our best to address all of the questions from the Zoom chat box and also from the Facebook Live. And for other further queries, you can always feel free to mail us at info@inhrr.org. I'd also like to convey my big thanks to all of our organizing team, our speaker, Dr. Upendra Baral, session moderator, Dr. Basanta Adhikari, our distinguished guests and participants for participating in this session. The session was really wonderful. We will be sharing the recorded session on our YouTube channel, and the links will be forwarded to the registered email address. We have a long way ahead, and we'll be happy to collaborate and coordinate with the number of organizations in the days to come. So before I end this, I would also like to share the same thing what Dr. Basanta has shared. We'll also mail all the registered participants regarding this upcoming our webinar. We hope to see you there as well. And the topic is especially focused on how mantle dynamics guided the main phases of Himalayan crustal tectonics. So I believe we'll have wonderful participation in that webinar as well. Okay, so with this, I would like to sign off from our session for today. Thank you, everyone. Thank you so much. Namaste, and have a wonderful time.
Namaste.
Thank you.
Thank you.